Uh, Good evening, everyone. So, I am Shubhanu Haldar. So, I am a PhD student at IIT Delhi. So, today we will be looking at the topics of union find and heap data structure. So, this is our week 5. So, as well as the last week. So, we will be trying to solve some questions which is very helpful for your assignment, solving your assignments and for your exams and quiz. So let's start today. So like the other days, so this is the first question. So I'll request everyone to try it by yourself first and then write your answer in the chat box, then we can start. Okay, so this is the question basically, that which of the following is an almost complete binary tree. So there are 4 options given, and among these 4 options you have to find the almost complete binary tree. So as you all know that heap is a binary tree, or this is a binary means they binary means it has 2 children, and or maybe it, if it has 3 children, it can be 3 array or n array tree. So and heap is a almost complete binary tree. So our main objective here is to know more about the heap data structure. So that's why we are starting from this point, which is almost complete binary tree, or we can tell it ACBT. Okay, so basically uh, a heap is a binary tree, or it can be said as 3 array tree or n array tree. Okay, so heap is ACBT. Okay, so what is a almost complete binary tree? So if we start from a very basic example, so you can see here that uh, this this is a almost complete binary tree. Okay, and if you see that with this is with two nodes, so this is almost complete binary tree. And if you draw with 3 nodes, this is almost complete binary tree. Okay, this is also a almost complete binary tree. So what does it mean by almost complete binary tree? That is, the leap can be present only in the last and the second last node, and leaps can be filled from left to right. Okay, so if this is the case, so this is not a almost complete binary tree, because it says that leap can be present only in last and second node. Prakash, hello. So this is not a almost complete binary tree. Okay, so if you see that this is also not a almost complete binary tree, because you have to start filling from left to right. Okay, so this is the concept. So if you see here, if you analyze the first example, that if it is a almost complete binary tree or not, so you can see that yes, C is the correct option. So because this is a almost complete binary tree, this is also a almost complete binary tree, this cannot be almost complete binary tree. Okay,
Excuse me, sir.
yes.
Sir, in option A, sir, the node containing 50 is greater than the root node 10. Then how it will be a binary tree?
Sorry.
Sir, node 50,
Yes, yes, this one.
sir, is bigger than the root node.
Yes.
How it will be possible? It will be not a binary tree, sir.
So what is the property of binary tree?
But the binary says, okay, sir, I have found the
Only
mistake, sir.
okay. So this is saying that binary tree as well as maxi. Okay. So I am saying that now let's try to find out which one is the ACBT, like which one is the almost complete binary tree. So this is a almost complete binary tree and this is a almost complete binary tree. But if you see that there is no left node, okay, so this is not a almost complete binary tree. And if you see, this should be in the leaf node, it should start filling from the left to right. Okay, so this is not a almost complete binary tree, so this is fine. Now the question is which one is a maxi. So our answer is like pretty fine, that our answer will be from A and C, because other two are not almost complete binary tree. Okay, so now let's see what is the property of maxi. So in property of maxi says that if all the root node will be greater than its child. So here we can see that you are right. So this is basically a mean heap. This one is a mean heap and this is a max heap. Okay, because this 40 and 50 is less than 20. So this 40 and 50 are the child, so this is less than 20, so this is a mean heap. But what is the property of max heap? That child will always greater than it, sorry, root node is always greater than its this is basically parent node or root node, so this will be always greater than the child node. So 55 and 42 are the child nodes. So 60 is greater than child node, 35 and 25 these are child node. So 40, which is the root node, is greater than child node, and from 60 and 40 70 is greater, so 70 will be a so 70 is a root node. So this option C is correct. So this is a this graph satisfies all the properties of the maxi. Okay, then come to our second question, that which of the following is are true? An almost complete binary tree in a mean heap tree if every parent node is minimum compared with its children. Okay, and second statement is an almost complete binary tree is a mean heap tree if every parent node is greater than its left child and less than or equal to its right child. Third option is heap sort is an in-place sorting technique and heap sort is stable. Okay, so these are the cases. So let's try to analyze. So in some previous lecture when we were learning about the sorting techniques, I described what are the in-place sorting techniques and what are the stable sorting techniques. Okay, so in place mean you know that there is no extra space required. Okay, so and stable means, so if mm, if for this array you have to sort, then your answer should be like this: 0 1a 1b 1c, then 7 8 9. Okay, so a this one should come first, then this one should come first. Okay, so this ordering should be there. Okay, so now you have to find out that this is a stable sort or not. Okay, so I think you all got the idea of stable sort. So let's try to analyze this from statement 1. Okay, please try to solve by yourself, then I'll show you. So basically, let's discuss uh, more more about this heap first. Okay. So basically, a heap is a heap is a basically kind of tree kind of structure. So it can have two things. That one is max heap and one is min heap. Okay. So in max heap, parent will be greater than child, and in min heap, parent should be less than child. Okay. So as I described that this is an example of min heap and this is an example of max heap. Okay. So uh, so now, so this heap property must follow two features. Okay. One is structural properties. Okay. And one is ordering properties. Fine. So these two properties should be followed for the heap. Okay. Now in heap there are some operations are there. Okay. Now we see how the operations are there. So there are so if this is a heap, we take any example. So basically you how you will be given that you will be given the array. Okay, suppose you are given an array 14, 24, 12, 11, 25, 8, 35. Okay, so what is the algorithm for this? That insert these keys one by one. So to insert this key you need order of one time. Okay. So time taken will be order of one only. Okay. And to insert a key into the into already constructed heap, in OR's case it should take log n comparison. Okay. So I'll show you how this works. Okay. So basically how it will come that so first 14 will come. Okay. Then first number is done, then 24 will come. So we know that this is a ACBT, so we will start from the left node. Okay. So what we want to do? So we want to make a max heap. Okay. So as a max heap, you know that parent node should be greater than the child node. Okay. So this will be exchanged. Okay. So then what will come here? So it will be like 4 will come here. Okay. Sorry. So 24 will come here. Okay. And 14 will come here. Then we'll go to 12. So 12 will be placed here. As you can see, this 14 and 12 both are smaller than 24. So this is okay. Okay. Now what will happen? Now 11 will happen. Okay. 11 will come. Okay. So 11 will come here. Okay. Fine. Now 11 is done. Now 25 will happen. So where 25 will be placed? 25 will be placed here. Okay. So now we can see that 25 is greater than 14. So this will be interchanged. Okay. So if this is this interchange, then what will come? That 24 will go here, 14 is here, now 12 is here, now 25 will come here. Okay. 25 will come here, 11 is here, 14 is here. So this child node is less than the parent node. This is fine. But if you see, you can see that this parent node 24 is less than 25. So what will again happen, that these two will again exchange its position. Okay, so what will come? So I so what will come, that 25 will come here. Okay, now 24 will come here, 12 will come here, 11 will come here, and 24 will come here. Now you will see 8. So 8 will come here, no problem. Now 35. So 35 will come here. Now what happened? You can see that 35 is greater than 12. So these 35 and 12 will be exchanged. Okay, if these two are exchanged, then what happened? See, 25, 24, 35, 11, sorry, 20, so this was 14, I think. This was 14. Yes. So this was 14. Yeah. So 35 will go here. Then 14 is here. Then 8 will come here, and 12 will come here. Now again you can see that this 35 is greater than 25. Then it's root node. So these two will again exchange, and our new heap will be generated. So what will be our resulted heap? So our resulted heap will be this one, 35, okay, 24, okay, 25, okay, 11, 14, here comes 8, and here comes 12. Fine, no problem. Okay, I think everyone understood this one, that how the trees, how can we build the max heap properties. Okay, how can we build a max heap and how can we build a min heap. Okay, now let's see that what are the properties here. Okay, so if you see that so what is the algo behind it. Okay, so algo is basically, so insert a key into heap. So if you take this first node, so you will insert in the heap. Okay, so this is fine. Okay, but so in the last case you saw that 35 was here. Okay, so 35 was in the last. So to insert 35 into its correct position, how many swaps and how many exchange you did. So you see that you from here to here you bring 35 here, then bring 35 here. Okay, so basically what is this? So as this is a binary tree, so what will be the height of the tree? So height of the tree is basically log n. Okay, so there are log n number of elements from root to this leaf, from root node to the leaf node. Okay, so you need total order of log n comparison, because you have to compare one element one by one and then swap. Okay, comparison and order of log n swaps. Okay, got it? So if there is total n element, then insertion will take n log n time. Okay, I think everyone got it. Fine. Now what happened? So now our motto was to see that it is a stable sort or not. Okay, so I think you all got the idea of how the Hippify is doing, how the Hippify method is working basically. Okay, so you can see that we don't need any extra space, so you can see that it is a in place sorting algorithm. Okay, so this one, so no extra space required. Okay, so this is a in place sorting algorithm, but is this a stable sort? So we can try with a simple example. So let's take 2 6 3a as these 3 came first, 4 then 3b as these 3 came second, then 7, then 3c. Fine. So now let's try to make a heap from 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 this given input. Okay, so 2 is here, 2 will come first, then 6 will come, then so as 6 will come, so what we can do that we can make the heap first. Okay, like we can do like this also. Rather than making it one by one, we first make the tree and then we will apply the Heapify algorithm. Okay, then 4, then 3b, then 7, then 3c. Okay, then if you apply the Heapify algorithm, okay, so from where you will start? So you have to start from the uh, so 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 what we will try to do. Okay, so you will try to build a max heap. Okay, so if you try to build a max heap, okay, so you can see that your this or if you want to sort this, so basically what you are doing, so we will sort using heap sort. Okay, so how you will be so so this is a heap, this is a tree, but how you will get the output of the sorting algorithm? So for this, what you have to do, that you have access only of the root node from the tree. Okay, and the last node of the tree. So this is the first node of the tree and this is the last node of the tree. So you have access of these two only. Okay, so then what you will do, that if this tree has been made, so these two will be interchanged. Okay, okay, so what comes here? So 3b comes here and 6 will come here. Okay, 6 will come here. Okay, so first what will come, that these two will be your outcome. So so I am considering this as a output of the heap sort. So you will access the root node and you will get 2. Okay, then what will come? So this 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 last node will come at the first. Okay, let's try by yourself that what will happen here. Okay, so if this 2 is the outcome of the sorting algorithm, then this 3c will be deleted from here and it will come here. Okay, so what will come, that this 3c will be here. Okay, and what will come, this 3b will be here and 4 here, 6 here, 3a here and 7 here. Okay, and then you have 2 is your output, then 3 is the root node, so it will then sorry, 3a, or which was the output, 3c was here, so 3c was here, so 3c will be your output. Okay, then so after 2 you got 3c as a result of sorting algorithm. Okay, so 3C will be deleted, then what will come? This 7 will come here. Okay, because 7 is the last node. Okay, so then how this T will look like? 7, 3B, 4, 6, 3, 8. Okay, fine. Then what will happen? So you can see that uh, this is a this is a this is not a mean heap. So heap, what will do, what will run, heapify algorithm will run here, and so what will come, maybe 3b will come here. So these two will be exchanged, these two will be swapped. So 3b will come here, 7 will come here, 4, 6, 3, fine. So you can see that after 2 3c has come, then 3b will be the output. Okay, so this should not be the case. So this will, so basically I am not following, so I am not uh, hmm, writing all these steps here. So you can see that after 2 3 3c 3b, okay, so like this, then 3a, then 4 6 7 will be the output of the array. Okay, so this is unstable. Okay, so what is this stable? If this is stable, then 3a should come first, then 3b should come first, 3c should come first, then 4 6 7. Okay, so heap sort is an in place sorting algorithm. This is correct. Heap sort is stable. This is incorrect. Okay, and what is saying that an almost complete binary tree is in a min heap tree if every parent node is minimum compared with its children. Okay, this is fine. Okay, and an almost complete binary tree is min heap tree if every parent node is greater than its left child. So here min heap, but what is saying, parent node is greater than its left child and less than or equal to its right child. This is also correct. So 1 2 and 3 is correct. Okay, so 1 and 3. Okay, let's analyze this one first, see what is happening here. So why 3 is not correct? That uh, an almost complete binary tree is a min heap tree if every parent node is greater than its left child and less than or equal to its right child. Oh, okay, first statement was correct, that parent node will be, the first statement was parent node is greater than its left child. This is correct, but less than or equal to its right child. So parent node cannot be less than or equal to its right child. So that's why this statement is not correct. So 1 and 3 is the correct statement. Okay, fine. So option C is correct. Okay, next go to our third question. So which of the following binary tree is a almost complete binary tree but not a complete binary tree? Okay, so can you write the answer in the chat? So I am waiting for your answers. Uh, which one is a which one is an almost complete binary tree but not a complete binary tree? So you can see here that if I write it, okay, so in an almost ACBT, I can say it like this, is in an ACBT, that last level is completely filled, then it is called, so if this is the case. So if the last level, so this is the last level, okay, if this is completely filled from left to right, okay, you don't have any option to put any element here, so then it will be a almost complete, then it will be a complete binary tree. Okay, so here you can see this is not a ACBT because you have to fill from left to right. Okay, then this can be a almost complete binary tree. So this can be our possible option, but this is a ACBT, this is the ACBT, but not a complete binary tree because this is not here, and this is also not a ACBT, not a complete tree. Okay, so this is a ACBT as well as complete. Fine. Now next question is, what is the worst case time complexity of heap sort algorithm? Yeah, because you are wrong, because you gave the answer as B. You can see that this is a ACBT, but not a complete binary because this node is not there. So you have to fill the last level. Okay. So basically for heap sort algorithm, what we do that we get element one by one. Okay, so for heap sort, this is n log n, you are right. So for heap sort, what we do, that heap sort we know that it is a in place algorithm, and this is unstable, we have seen earlier, and the thing is n log n. Okay, this is the time complexity, but why this is n log n? So this should be clear. Okay, like if you see anything any option, like if you take a simple example of like 4 6 10 9 2. Okay, so what you will get after sorting this one, you will get 2 4 6 9 10. Okay, so after sorting you will get this. So what you will do, you 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 need ascending order. So you will make a min heap because you have access of the root node of the min heap. Okay, so what we'll do, we'll make a heap here. Okay, 4 6 10 9 2. Okay, so how much time you need basically to make this tree? You need order of n time. Fine. Is it clear, like why order of n times? Because you have just made a tree, and one by one element you go to one by one element and just inserted the element here. So you need order of n times only. Okay, so I have just inserted it. I saw 4, I inserted 4. I saw 6, I inserted 6. I saw 10, I inserted 10. Okay, I saw 9, I inserted 9, then 2, then 2. Okay, I just followed the thing that okay, uh, heap is a almost complete binary tree. Okay, so I followed the left to right policy. Okay, this is fine. This one need a order of n time. Okay, now what we'll do, what we want to do, we want to create the mean heap. So for the mean heap, we know that mean heap follows the parent node should always less than the child node. Okay, so if you see here that this 4 is fine, okay, but see here that this 2 is this 2 is less, but this parent node 6 is greater than 2, so this will be extended, okay. So what you will get, you will get 4 2 10 then 9 then 6. Now it is fine. Now you can see this that this 2 is less than 4, so 2 will move here, okay. Then what we will get, we will get 2 4. So basically what you are doing here, you are applying heapify method, okay. So you are applying heapify method on each and every element, okay. So here 9 6. So what, how this happens, so basically uh, the how the algorithm works, that each it goes to it, because you have access to the root node, so it first goes to the root node, okay. Then it checks here, then it checks that, check your parent, so this is the parent, so it checks, see your left child and your right child is less than you or is greater than you or not, because we want to make the meaning. So 4 checks that okay 6 is greater than me and then 10 is greater than me. Then what is do, then it recursively call is its left child and right child. So if it recursively call, then it will come to 6 and 10, as 10 has no element, so it will stop here, so it will come to the left child. So then 6 will check its left child and right child, is it greater than me, is it less than me, is there anyone who is less than me. So it see that okay yes 2 is less than me, okay. So a swap occurs, so this one 2 goes here and 6 goes here, okay. So if a swaps occur, then again it will check that, as this is a result, as this swap occurred here, so it will check that its parent node, so it checks its parent node again, that is it a as is I am is it my position that my child is my parent is less than me or not. So this is how the algorithm works basically, okay. So this is fine. So as you this heap will come, okay. After heap 5 you will get this heap. Then how you will work, so you have access to the root node, so 2 will come out, okay. In the output 2 will come out, okay. And then this is the last element, so this 10 is the last element, so 10 will go to the uh, uh, 10 will go to the root node, okay. So what will happen, that 10 will come here, okay. Then 4 9 6. Now you see that it will again heapify it, okay. Then because you can see that 4 is less than 10, so this doesn't satisfy the min heap property, so it will come like this 4 9 6, okay. So now again see, this doesn't also satisfy the min heap property, so what we will do, 4 fine. So now this is sorted, so this is a min heap. So then you have access to the root node, so 4 will come here, okay. As 4 is coming here, then 10 will also go to the root node, then 10 will again come here, then 6 then 9. Then what will happen, that this doesn't follow the property of min heap, so 6 will come here, 10 will come here, 9 will come here, this also doesn't follow this, okay. So 6 9 10 6 9 10 6 9 10. So this will be your answer, okay. So you can see that altogether we need for we need order of n time for the building the heap, and n log n time, because order of height of binary tree was log n. So log n. So for n element we need n log n time. Okay. Now the question is, which of the following data structure is best suited for the heap sort? So the options are array, singly linked list, doubly linked list, and double-ended queue. So you know the queue. So this is a double-ended queue. So you can insert from here. Also you can insert from here. Okay. So insert and exit, like insert and deletion, can happen in both ways. So this is a double-ended queue, and one is array. So in array representation, so what we can see that if we make a heap, max mean heap, basically 2 6 9 10 11, so this is a max heap. Okay. So in array, how I will store it? So I will store like 2 6 9 10 11. Then what will be the index? So this is 0 1 2 3 4. Fine. So these are the index. So if you see, so this is the parent node. Okay, P1. Okay, and 6 is the left child and 9 is the right child. Okay. So you can see, if this is a ith position, then left child is at 2i plus 1 index, and right child is at 2i plus 2 index. Okay. So we can grow the tree. 12 13 12 13. So like this. Okay. So if you see that I is equal to 0, at I is equal to 0, then 2 is there. Okay. Say, so this is parent node. So what is at left tree, and what is at left child, and what is at right child? So 6 is at right child, and what is its position? 0, and this is 1 1. So 2 into 0 plus 1, and this is 2 into 0 plus 2. Fine. This is 2. Fine. Now what is the now for this node, for 6? So 6, what is the value of I? I is equal to 1. Okay. And so this is the parent node, and what is the left node, and what is the right node? So left node is 10 and 11. Okay. And 11. So 1. So 2 into 1 plus 1, 2 3, and 2 into 1 plus 2, 2 4. So let's check that. Okay, yes, 3, the left child of 6, is at 2i plus 1 position, and 2i plus 2 position. Fine. Then for 9 also, 2i plus 1 position and 2i plus 2 position. Got it? So this one, like, what is the children of 9? 12 and 13. Okay. So 9, 12 and 13. So what is the position of it? 4 5 6. So 2 into 2 plus 1 and 2 into 2 plus 2. Fine. So array is the very best representation of the following structure of heap sort. Okay. So if you come with a linked list, so what happens? So if you come with a linked list, so what happens? you have to, so in order of n memory we can store it. Okay, so for linked list, so you have to basically store each and every element first, 2 6 9 10 11 12 13. Okay, 9 10 11 12 13, then you have to point it which is right one and which is left one. Okay, then you can see that yes, actually this is a very bad representation for doubly linked list also. Okay, so array is the best one for the storing the heap. So now second question is, which of the following is true about the heap data structure? Priority queues can be efficiently implemented using binary heap, and heap data structure can be used to efficiently find the kth smallest or largest element in an array. Okay, so as you so let's go back to our thing. So I show you here that we have access to the root node and we have access to the last node. Okay, so uh, so delete, so basically insert mean you inserting an element. So there are four operation possibles here. Okay, so for heap short, uh, so we can, so what are the priority queues? So basically you are designing a CPU. Okay, so there are some kind of works. Okay, so which is a high priority work and then there is a low priority work. Okay, so basically this is the priority of first priority, second priority, third priority, fourth priority. Okay, then you have multiple number of works, multiple instances of work. Okay, maybe you are gaming and you are chatting with someone. Okay, so there is a input output and your gaming output. So you are doing a multiple task, performing multiple tasks in your CPU. So some task has more priority than other task. Okay, so that's why in CPU this is implemented, there is implementation of priority queue, that this is a queue kind of structure uh, because this is of first priority, but this task should be end one after another, because this came first so it will finish first, this came second so this will finish, if this came then this will finish. Okay, so first first so as a queue, so if you are in a queue, or if you are if you if you have gone to any concert and you are in a line, if you are in a queue, then you have to go one by one. Okay, so this is the basically story of the priority queue. So priority queues can be efficiently implemented. So this, if we want to implement this kind of queue, so we can use the binary heap structure, because for binary heap four kind of operations are possible. প্রকাশ, পিছনের ল্যাপটপটায় চালিয়ে দে তো। হ্যাঁ, so if you want to implement this priority queue, so for binary heap, so what are the possible cases that you can do insertion. So I have shown you the insertion. Okay, and insert operation basically. So this is a insertion operation. Then you can do delete operation. You know how to delete it. You know how to extract the maximum element, extract max. Okay, and the decrease key. Okay, So and all the operation are in order of log n time. Okay. And order statistics basically is heap data structure can be used to efficiently find kth smallest or kth largest element in an array. Okay. So method, so how if you want to get the kth largest element, so how you will do it, like build a max heap. Okay, so follow this one, that build a max heap which is of order of n. Okay, then use extract max k times to get k maximum element from the max heap, which will take k log n time, and complete it in n plus k log n time. So as this is a big O of n plus k log n, so it will basically take big O of n log n. Okay, I think this is clear. So option C is correct, both 1 and 2 are the correct. Now let's check the next question, that the pre-order and post-order traversal of a binary mean heap constructed by inserting this element into a empty mean heap. So what will be the, so you have to make a mean heap. Okay, and what you have to do, you have to then uh, basically find the pre-order traversal and post-order traversal. So please try to find this one by yourself first. So what is there? With 32, 32, 15. So what is the input? What is our input? Input is 32, 32, 15, 20. 32, 15, 20. Okay. 30, 12, 25, 16. Okay. This is our input into an empty mean heap. Okay. So from this input we have to make a mean heap. Okay. So 32 will come first, as you know. Fine. Then what will come? Then 15 will come. Okay. Then where will you place it? 32 will come here and 15 will come here. Okay. But you see, this is a mean heap. Okay. So you are violating the properties of mean heap. So that's why this will be swapped. Got it? So this is not a property of mean heap. So that's why it will swap. Okay. 15 will come here and 32 will come here. Fine. Now what we will do? So this is a mean heap. Okay. Now 32 is done, 15 is done, then 20 will come. Then 15 here, 32 here, 20 will come here. Then what will happen? 30 will come. Okay. Then where we will place 30? 30 we will be placing. So this 30 will come here. Okay. So is this following the mean heap property? You can see that there is a violation of the mean heap property. So in these two, this 32 and 30. Okay. So that's why what will you do? You will swap these two. Okay. So 15 will come here, 30 will come here, 20 is here, and 32 is here. Okay, fine. Now this is following the mean heap. Okay. So I am trying to write the each and every step so that you can understand. Okay. Now what will come? That after 32, 12 will come. So where 12 will be placed? 12 will be placed here. Okay. So you can see that there is a violation. So there is a violation, 30 and 32. sorry. 30 and 12, because 12 is minimum, so it will be so part 11, 15 will come here, then 12 will come here, then 32 is here, 30 is here. Okay, got it. 20 is here. Okay, now what will happen, you can see that there is again a violation. The 12, sorry, this 12 and 15. Okay, so what will happen, the 12 will come here, 15 will come here, 20, 32 and 30. Okay, then what will happen, is this a min heap? Yes, this is a min heap. Okay, then so we can add the next element. What is the next element? 25. So where can we add? We can add here 25. This is fine. Then 16, where can we add 16? We can add 16 here. Now you see that yes, there is a violation. 16, and 20 is a violation. Okay, so you can see here that, so this is the, so this will be our last. Fine. Now what we got the tree, which is so let's draw our final product. So our final product is 12, 15, 16, okay, 32, 30, 25 and 20. Okay, so now you have to do two things. One is pre-order traversal and post-order traversal. So in pre-order traversal, what we do, that we check the root node first. Okay, whenever we see a node, we write it. So 12, we write it, then 15, we write it, then 32, we write it, then we have seen the 15, then we have seen 30, we write it. Okay, then what comes, 15 we have already seen, 12 we have already seen, we see 16, we write it, then 25, we write 25, then we see 20, we see 20. Okay, so this is the pre-order. Okay, so this is the pre-order. Okay, and what is the post-order traversal? So for post-order traversal, what we do, whenever we see the element for the last time, then we will write it. So this is the post-order. So 1 we have seen first time, 15 we have seen second time, so 32 we have seen first time, then second time, then we have seen 32 for the last time. So we will write 32 here. Okay, then we go here, 15 I am seeing 15 for second time, 30 I have seen for first time, now second time, now third time. Okay, I will write 30 here. Okay, fine, are you getting my point? Then 15 I have seen 15 for last time, then I will write 15 here. Then 1 I will seeing 1 for second time, 16 for first time, 25 for first time, 25 for second time, 25 for last time, then I will write 25 here. Now 16 for second time, 20 for first time, 20 for second time, 20 for last time, then I will write 20. Then 16 for last time, 16 I will write here, then 1 for last time. So these two are the answer. Okay, let's see which is the answer. 32, 30, 15. So post order 32, 30, 15. Okay, so I think C is the right answer. Let's check the answer. So C is the right answer. This one. Now next question is, the minimum number of interchange needed to convert the array into a max heap. Okay. So minimum number of interchange needed. Okay. So please, I have shown so many example of the min heap and max heap. So please try it by yourself and tell me that how many number of swap is required there. Okay. So first what you will do, you will make a tree. Okay. 89. Okay. 19. Okay. 40. Okay. 17. Okay. 12. Okay. 10. 2. 5. 7. 11. 6. 9. 17. Okay. So this tree has been made. Now you will try to swap. Okay. So from where you will start? So what you have to do, you have to find out a max heap, not a min heap. Okay. So start from the last child. See this is in a the correct position or not. Okay. So for the max heap property, what you know that child should be less than the root. Okay. So what you will do, so you will interchange this one. So how many swap you need? So till now we need one swap. Okay, to interchange 10 and 70. Fine. Okay, so what I will do, I will interchange these two. Okay. 10 will come here and 70 will come here. Okay, 70 will come here, 10 will come here. Fine. Okay, now you see that 70. So is this satisfying the max heap property? The 40 is less than its child, so this is not satisfying the property. So what I will do, I will again do the second swap between 70 and 40. Fine. So these two will be interchanged. So what I will do, 70, 40. So 70 will come here and 40 will come here. Okay. Now this all are sorted, I think. Okay. Now check one. Okay. Now please try to write the answer in the chat box, that if this is a max heap or not. Okay. And how many swap required. Yeah. So because you are right, so only two swaps are needed. So this one is the right answer. It's 2. I've also written that one swap to swap 10 and 17, second swap to swap 7 and 40. Right. And this is a max heap. Okay. So next question, that how much time it takes to insert an element into a max heap or min heap which already contain an element. So what is the question? How much time it takes to insert an element into a max heap or min heap which already contains an element. Okay, so you can see that this one, how many element we have? We already have n element. Okay. So an element is equal to, how many elements we have? 1 2 3 4 5 6 7 8 9 10 11 12 13 14. 14 element we have. Okay, now I will be adding the next element. So where should I add? I will add here. So which element I should add? Maybe 97. Okay, so I am adding 97. Where in a max heap. So it was a max heap. Okay, from our last question. So this was a max heap. So in this max heap I am adding one element which is 97. Now what is our question? That our question that how much time it takes to insert an element into a maxi. So we have inserted it, but this is not a maxi. So what should I do to make it a maxi? So I'll try to heapify it. So let's find out that how much time heapify method takes. Okay, so to heapify this one, so what you have to do, you don't have to check this part. Okay, so you have to check. So what you have to do basically, so you have to from this element, so you have to check this one. So these two will be swapped. Okay, okay, now 97 is here. So now then again you will check this 70 and this 97. Okay, so 97 will come here. Okay, you will check this 70 and 97. Okay, then 97 will come here, then you will check 97 and 89. So these two will be again swapped. So you will check till the height of the binary tree. So what is the height of binary tree? So height of binary tree is basically log n. Okay, so okay, fine. So this is the worst case. Okay, okay, fine. So 97 is the worst number. Okay, so if I add a small number here. Okay, so 97, if I add 1 here. Okay, so do I need a, so to insert 1, how much time I need? I need only order of 1. Okay, just to insert 1. Okay, or only order of 1. Then do I need to heapify it? No, I don't need to heapify it because it is already small from its parent node. So that's why best case time complexity, so here you can see the best case time complexity is omega of 1 and worst case is order of log. So option B is correct one. Got it? Now see the next question. Please try to find the answer. Yeah, let's see. So basically this question is about greedy algorithm. Like in the last class we have also seen that what is the greedy algorithm. We have seen the decast algorithm and all. So we have to see that which one is a true greedy approach. So a greedy algorithm always makes the choice that looks best at the movement. Okay. So this question is here because we will be solving the Kruskal algorithm based on the greedy approach. Okay. So basically, in last class I show you that how the Kruskal algorithm is working. So using the example of islands and all. So second is greedy algorithm always yield optimal solution. Decasta algorithm for shortest path from single source is one of the application of greedy approach. So let's analyze first. So a greedy algorithm always make the choice that looks best at the movement. That is, it makes a locally optimal choice in the hope that this choice will lead to a globally optimal solution. Are you getting it? That greedy algorithm makes a locally optimal choice in the hope that this choice will lead to a global optimal solution, but it 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 doesn't mean always. Okay. And uh, and as the second option says that greedy algorithm always yield optimal solution. Okay, greedy algorithm doesn't always yield optimal solution. Maybe some certain cases, okay, it yield optimal solution, but not for all cases. Because of this reason specified in one, greedy approach do not always yield optimal solution, but for many problem they do so. And decasta is the application of greedy approach. So these two option from these two options, this option is not correct. So only option 1 and 3 are is correct. So option B is the correct one. Okay. Now this is the next question, that suppose we want to extend the union find data structure to support the operation reset C, which takes as input in the name of component C and then breaks up C into singleton components. Make union find. For instance, C is equal to 3 and C currently consists 137. Then reset C will produce 3 component called 137 containing 1, 3 and 7. So in the union find data structure, so what union find do? So you know disjoint sets and all. So the union find data structure support 3 operation on collections of disjoint set. Okay. Let n is the size of the universe, like including all elements. Okay. Then what operation we perform here? We perform create set u. Okay. So how much time it takes? It takes order of 1 time, because create set containing the single element u. Okay. So as there is only single element, so it takes order of 1 time. Then find set. Okay. Find set. So you have to find the element u. Okay. Then find set containing the element u. So find set. So it takes log n time. Then union u and v. Okay. How much time it takes? It takes log n time. Okay. So in union, what it does basically, it merge the sets respectively containing u and v into a common set. Okay. So these are the basically option. Okay. So the basic idea of this basically uh, how can I say that this is a up tree kind of implementation. Okay, so what is a up tree? I think this much is clear, then we'll see the next thing. Okay, so so what is the up tree implementation? So every item is in a tree. The root of the tree is the representative item of all item in the tree, and the root of the tree represent the whole item basically. Okay, so in this up tree implementation, every node except the root node has a pointer pointing to its parent, and the root element has a pointer pointing to itself. So what happened basically? So if this is a if this is a root node, okay, so basically a b c, fine. So everyone is pointing to its parent node. Okay, everyone is pointing to parent node, and the root node pointing to itself. Got it? So x, y. So x is y is pointing to it, but x is a, so these two are two separate tree. Okay. So how the create set operation is happen, that that is create set x. How it is happen? That create set x to parent is equal to x. Got it? Now, how find set operation works? So it said that the operation of find set x is easy. We simply trace the parent point until we hit the root, then return to the root element. So how this is happen basically in code? How we'll write the code of the find set x. So this is a tree implementation. While x not is equal to x parent. Okay, so basically until x is not a root, x not pointing to itself only. Okay, until then what we will do, x is equal to x parent. Okay, and then return x. So this is the formula. Okay, uh, now the operation of union xy is a little bit tricky one. We can just simply putting the parent pointer of the representation of x pointing to is representation of y. So basically what here happens basically, how this happens, so this e goes up, and what happens basically, x come here, y is here, it is pointing this, and it point to itself. So this is the basically the union operation. Got it? Okay, so how we implement the union operation? So we implement the union operation, union xy. If we do this, so a is equal to find set x, b is equal to find set y. If a dot height less than is equal to b dot height, then if like check height of a, sorry, check height of a basically, check the height of a and check the height of b. So if height of a less than height of b, then what you do, then you check that a dot height is equal to b dot height or not. Okay, then b dot height plus. Okay, then what we will do, we'll do parent of A is equal to B. So you are doing parent of E is basically now X. Okay, then else what you do? Sorry, else this else what you do? B parent is equal to A. Got it? So this is how you are doing. Okay. So the question is now that suppose we want to extend the union find data structure to support the operation reset C. So what is reset C? So reset C takes an input as input the name of a component C. So C is a component. So we have some component, okay, like this. So this is a like X, Y, Z, PQ. So these are the component. So this component name is A, this component's name is B, and this component name is C. So it takes the input of a component and then breaks up C into singleton component like make union find. So what is do? So if so what reset A will do? Reset A will make it a singleton component like A, B, and C. Got it? So it basically breaks up into like this. Got it? Yeah. So this is the work of reset C. So it's break into 3 partition. Okay. Reset A. Okay. Got it? Now, for instance, if C is equal to 3 and C currently consists of 137, so instead of 137, we have taken ABC. Okay. So this option reset C is B. So which of the following is correct about the cost of adding reset C to the array and pointer implementation of union find discussing at that lecture? Okay. So in lecture, sir discussed about the array and pointer representation of union find. In the array representation, you can see here, in the array representation, we have the list member C, which allows up to update the content of C in time of order of size C. Okay. So basically, if there are 3 elements, okay, 3 elements are there, like so like 137 was there, so it was breaking up like 1, 3, and 7. Sorry. Okay. So what you have to do here? So for array representation, you have to check the array only. Okay. Okay. So how much time this need? You need order of n time. Okay, or order of size of C. Okay. So in the pointer representation, there is no easy way to identify all elements that belong to component C without scanning the entire set. So it makes order of n time. Got it? Order of n means order of universe. Means if there are you can see if there are 8. So for array representation, for this case, for this case, okay, I'm talking about this case. If we have 8 elements like this, okay, A, B, C, X, Y, Z, P, Q. So for array representation, we have the representation of the array. Okay. Okay. So we can go to the each element, we can access the each element. So that's why we need order of 3 times, because we can access C, B, A in order of 3 times. Okay. But if we have a pointer representation, okay, we have we have the pointer to the first element only. Okay. 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 So then we have to check the whole universe. So we need order of n or order of 8 times. Okay. So this is the case that for array representation, order of size C, and pointer representation, order of n. So I think C option is correct. So option C is the correct one. Okay. So for array representation, order of size, pointer representation, order of n. Okay. Now the second question is, in the algorithm presented for the closest pair of points problem, we have assumed that no 2 points have the same x or y coordinate. Okay. the following step would become more complicated to justify without these assumptions. Okay. So in the lecture you have seen these two things basically. So closest pair. So in the lecture you have already watched the video of the closest pair. Okay. So from there the question has arrived. So this is the question from the previous quiz, basically previous year's quiz. So this closest pair point is the basically a algorithm developed for the divide and on based on divide and conquer approach. So basically the example the sir gave there, so that is basically several if there are several object on the screen, okay, like this. So what you will do, so you will go for so there are, if there are n objects, so naive algorithm will be for each pair of object compute their distance. So you will be computing the distance between these two, these two, these two, these two, okay. Then what we will do, so this is done. Say what we will do, that you will try to compute the distance with these two from this. So total order of n square time you need, okay, got it. So from each pair, for each pair of objects you will compute that distance, then report the minimum distance over all such pair, okay. So there is a clever algorithm based on divide and conquer, divide and conquer, which takes order of n log n times. So you know that order of n log n is less than order of n square, okay. So a point P is given by xy coordinate. So if this is a point in my screen, so, so this is a point in my screen, okay. So how I can, so this is xp, like x1 y1 like this, x2 y2, x3 y3, x4 y4, and x5 y5, got it. So if there are given inputs, if I want to find the distance between these two, so what I will do, so I will be do, so what will be the distance will be root over x2 minus x1 whole square plus y2 minus y1 whole square, fine. So this is how we will calculate the distance. So if there are n points given p1 to pn, find the closest pair. Assume no two points have same x or y coordinate. So brute force is uh, n square we know, okay, fine. Now in one dimension, if this is in one dimension, then what will be the d will be basically pj minus pi, got it. Fine. So so what we can do for one dimension, I can, what I can do, so if this is a one dimensional point, like if this is like this one, okay. So what I can do, so I have x1 x2 x3 x4 xn. So I have to find the distance between it. So what I do, I sort it, okay. So if I short it, if I short this point, so maybe I use heap sort. Heap sort takes order of n log n time, okay. So after n log, so I first what I do, I sort the points, it takes order of n log n times. Then what I do, I compute the minimum separation between adjacent point basically. Hello. হ্যাঁ হ্যাঁ আচ্ছা তুমি আমাকে একটু 8টার পরে ফোন করবে, আমি একটু ক্লাস নিচ্ছি। কবে আছে তোমার ফেস্ট একবার বলো তো আমার। ওকে ফাইন ফাইন, থ্যাঙ্কস থ্যাঙ্কস। So, uh, so this is the case. This is the case for 1D representation. Okay. So now the question is like I am not going to the details of the 2D representation and all, because already uh, in your video lecture, so there are the answers of 2D representation. So now the question is, in the algorithm presented for the closest pair of points problem, so we have assumed that no two points have same x, y or y coordinate. Okay. Which of the following step would become more complicated to justify without this assumption? So what should be the answer? So all x coordinate could be the same, in which case we may need order of n time for each point py to assign it to qy or ry. So constructing qy and ry from py, order of n in the divide step. Okay. So this is the answer. Fine. Now this is the next question. Okay, suppose we want to support the operations predecessor and successor in a heap. Given a value v in the heap, pred v tells us next smaller value currently in the heap, and sux v tells us the next larger value currently in the heap. Okay, so the question is, in both min heaps and max heaps, both operation takes order of n time. Okay, so what you have to do, that here the question is, they are trying to find, they are trying to implement two new operation, pred v and suck. Okay, so what is, like, if you like this, if you have a mean heap, okay, 9 2 3 5, so this is an example of mean heap. Okay, and what is the example of max heap? So sorry, this is the example of max heap, and what will be the example of mean heap? Like 2 3 7 14 9. So this is an example of, and so this is 5 and 7. So this is the example of mean heap, this is the example of max heap. Fine. Now this spread function tells us the next smaller value currently in the heap. Okay, next, so maybe there were some element where we're doing the heap sort. So now our heap structure is this. So pred v tells that what is the next smaller element. So if we use the mean heap, so you can see that only the root element is the smaller element. Okay, so for a mean heap, if this is a mean heap, okay, in order of one time I can say what is the next smaller element. Okay, and also if this is a sag b says that what is the next larger value. So for max heap, in in order of one time, I can say what is the next maximum value. Fine. Fine. Is it clear to everyone? Okay. Now, if this is a max heap and this is a min heap, so in the max heap, in how much time I can say that what is the next successor value, like what is the in max heap. So if this heap is given, in how much time I can say this is the next smallest element, like smallest after the element. Okay, so what will be the case? So you can see, in best case it is order of 1, but if you want to find these two, okay, you have to scan the whole array. Okay, so if this heap is represented in an array form, so it will take order of n time. Okay, so for min heap case also you have to scan the whole whole heap structure, or so this is a pictorial representation, but how it is represented, it is represented in a array form. Okay, so I is basically the parent. Okay, and the left child is basically 2i plus 1, and the right child basically the 2i plus 2. Okay, so this is how you can access the child and parent from the array. Okay, and so for max heap you will take order of n time. For this also you will take order of n time. Okay, got it? So in both min heap and max heap, both operation takes order of n time. So this is the correct answer, I think. Okay, in both min heaps and max heap, both operation take order of n time. Yes. So now consider the min heap. Okay, this is a min heap 12. This one build by repeatedly inserting values into an empty heap. Okay, so which of the following could not have been the last element inserted into the last element inserted into the heap? So you have two options to insert into the heap. What you can do, that you can write like this: 12, 27, 48, 30, 37, 79, 54, 43, 39. Okay, first you insert like this in a tree structure. Okay, so here what happens, that after building this tree, you apply heapify method. Okay, you apply heapify method. Okay, to make it a heap. So what kind of heap you have to make? Like min heap. So you have to make min heap. So this is not a min heap. Is it a min heap? 54, 44. So this is a min heap, but this is by inserting the element. So so what here they are telling to say, they are telling to do us, like, do it one by one. Okay, but by repeatedly inserting values into an empty. Okay, so what we'll do, so we'll do 12, 27, fine, then we'll do 48, fine. So if you see, the last position added the one containing 39. So last position is 39. So let's try by yourself this one. So basically last position is the 39. So which of the following could not have been the last element inserted into the heap? So you see that 39 could have been inserted into this list because 39 is last. Okay, so you can see that this 12, if you see 27, so 27 could not be the last element. Okay, otherwise it could have here. Okay, in the right side. 30, 30 could not be the last element because 39 is here. Okay, so 37, 37 is here. So 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 what could have happened? That 27 is here. If 27 is here, then it will go here, then it will go here. So this could happen. Okay, so I think I am like what we are doing, what we are trying to do. 39 is here. So the question is, which of the following could not have been the last element? Okay, so 39, so if you see option D, 39 could be a last element. 39 is a last element. Okay, so if 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 option check option one by one. If 27 is here, so 27 can go here, then go here. 27 could be a last element. Okay, 30, so if you check 30, if 30 come here, 30 can go here. Okay, 30 could be a last element. Okay, but if you check 37, if 37 is the last element, it cannot go here. It could have go to the root. Okay, got are you getting my point? So if 37 is here, if 37 is here, 37 could have go here, or go here, or go here. Okay, but it should not be in this position. So 37 cannot, could not have been the last element inserted in the heap. Got it? So now this is our last question, that suppose we implement merge sort with a 5-way split. Divide the array into 5 equal parts, sort each part, and do a 5-way merge. What would the worst case complexity of this version? So you know about the merge sort, that merge sort recursively breaks down the arrays to sub arrays of its half size. Okay, so merge sort basically consists of one algorithm, which is the merge option. Okay. So similarly, three-way merge sort breaks down the array into subarray of 1/3. Okay, like if this is a merge sort, so merge option basically break down, and this is part A and this is part B. Okay, so if this is a three-way merge sort, then this is part 1, part 2, and part 3. Okay, so here you have what you have to do. You have to make it five way. Okay, so this is a, so you have to do a five-way merge sort. What we'll do, we'll take a array and make it 5 part. 2, 3, 4, 5. Got it? Okay, so what will happen, that so this is obvious that you can think that this will take less amount of time. So what is the time taken by merge sort algorithm? That is n log n base 2. Yes, is it? So it would be same as the time complexity when we are dividing the problem to halves every time. So only the base of log changes. But when we divide array into two sub arrays, then two-way merge needs one comparison, but three-way merge needs two comparison. So although by splitting arrays into three sub arrays, we are decreasing fewer number of passes. We are actually increasing the cost of each pass by doing more number of comparison. Okay. So what we are doing basically, Tn is equal to 5n by n by 5, is not T. Okay. So basically what is happening, order of n log 5n, this is happening here. Okay, so other way you can see here. Okay, so basically so this is the case, like, so this is the time complexity of the algorithm. Okay, so for 2a merge sort, what was the case? For 2a merge sort, you are merging it. Okay, you are breaking it into two part. Okay, and merging it. Okay, so this was the case. For 3-way merge sort, what will happen? 3t n by 3 plus order of n. Okay, so this is basically order of n log 3n or order of n log 2n. Okay, so this is the answer. So which one will be the correct answer? N log n base 2, this one. Fine. So okay, so this was our last question. Okay, so I think you have learned something from this lecture. So thank you for joining. Okay, we'll meet in the next week. So do you have any question about anything? You can ask now. Okay, fine. Thank you everyone for joining. Okay, we'll meet at next week.